What specific problem does the token bottleneck, ToBo method address in sequential scene understanding, and why is this problem significant in the context of robotic manipulation?
The token bottleneck, ToBo method addresses the problem of effectively summarizing observed scenes while recognizing temporal evolution in sequential scene understanding. This issue is significant in robotic manipulation because traditional self-supervised learning methods, such as May and May, struggle with capturing dynamic transitions and fail to provide cohesive representations necessary for predicting actions based on visual states from consecutive scenes. ToBo's design, which involves compressing a reference scene into a bottleneck token and predicting a target scene using minimal hints, ensures that essential information is preserved and temporal dependencies are embedded. This capability is crucial for robotic tasks, as it allows robots to make informed decisions based on a comprehensive understanding of their environment, leading to improved performance in manipulation tasks. The method's effectiveness is demonstrated through significant performance gains in both simulated and real-world robotic environments, highlighting its importance in enhancing robotic interaction with dynamic surroundings.
How does the proposed token bottleneck, ToBo method work? Please illustrate the methodology step by step, including details of the squeezing and expansion processes. This is extremely important.
The token bottleneck, ToBo method operates through a two-step process, squeezing and expansion. In the squeezing step, a reference scene is compactly encoded into a single bottleneck token, which captures essential information from the scene. This is achieved by patchifying the reference scene into non-overlapping patches, which are then processed by an encoder to generate spatial representations, with the CLS token serving as the bottleneck token. In the expansion step, the model predicts a subsequent target scene using this bottleneck token, along with a minimal set of patches from the target scene as hints. The high masking ratio applied to the target scene forces the decoder to rely heavily on the bottleneck token, thereby ensuring that the essential information is preserved and enabling the model to recognize temporal dynamics interleaved with the hints from the target scene. This design ultimately enhances the model's ability to summarize observed scenes while effectively capturing temporal evolution.
Can you provide a simple, illustrative example that demonstrates how the ToBo algorithm operates, including the key steps and the rationale behind them?
The token bottleneck, ToBo algorithm operates through a two-step process, squeezing and expanding. In the squeezing step, a reference scene is compactly encoded into a bottleneck token, which captures essential information from the scene. For example, if the reference scene depicts a robot in a kitchen, the bottleneck token would summarize critical visual elements like the robot's position and the objects around it. In the expanding step, the model predicts a subsequent target scene using this bottleneck token, along with a minimal set of patches from the target scene as hints. This design compels the model to rely heavily on the bottleneck token, ensuring that it preserves vital information while also embedding temporal dynamics, which is crucial for tasks like robotic manipulation. The rationale behind this approach is to enhance the model's ability to summarize observed scenes conservatively, while effectively recognizing temporal changes, ultimately improving performance in sequential scene understanding tasks.
What are the theoretical and practical benefits of using the token bottleneck method compared to existing self-supervised learning frameworks for visual representations?
The token bottleneck, ToBo method offers significant theoretical and practical advantages over existing self-supervised learning (SSL) frameworks for visual representations. Theoretically, ToBo enhances the conservative summarization of observed scenes while embedding temporal dynamics, which is crucial for sequential scene understanding. This is achieved by compactly encoding a reference scene into a bottleneck token and predicting a target scene using minimal hints, thereby ensuring that essential information is preserved and temporal dependencies are recognized. Practically, experiments demonstrate that ToBo outperforms conventional SSL methods, such as May and May, in various sequential tasks, including robotic manipulation and video label propagation, achieving over 20% improvement in success rates in simulated environments. Additionally, ToBo exhibits strong generalization capabilities in real-world applications, showcasing its robustness and effectiveness in transferring learned representations to unseen environments.
How did you validate the effectiveness of your method, and what experimental designs, datasets, and metrics were employed to assess its performance?
We validated the effectiveness of our Token Bottleneck (ToBo) method through comprehensive experiments across various sequential understanding tasks, including video label propagation and vision-based policy learning for robotic manipulation in simulated environments. We employed datasets such as Kinetics 400 for pre-training and evaluated our method on benchmarks like Franka Kitchen, RLBench, Adroit, MetaWorld, and DeepMind Control Suite, DMC. Our experimental design included fair comparisons with established self-supervised learning baselines such as SimCLR, Moco V3, Dino, May, and dynamic scene methods like SciAm-May and RSP. We measured performance using success rates in robotic tasks and reconstruction accuracy in video label propagation, demonstrating significant improvements, over 20% in some cases, compared to the baselines. Additionally, we conducted qualitative analyses of robot trajectories in real-world tasks, showcasing the robustness and transferability of our pre-trained models.
Considering the limitations noted in the paper, what are the key constraints of the Token Bottleneck method, and in what scenarios might it underperform or struggle?
The Token Bottleneck (ToBo) method, while effective in sequential scene understanding, has certain constraints. One key limitation is its reliance on a high masking ratio during the expansion step, which may hinder performance in scenarios where precise reconstruction of target scenes is critical, as the model must depend heavily on the bottleneck token. Additionally, while ToBo captures essential scene information and temporal dynamics, it may struggle in environments with highly complex or unpredictable dynamics that require more nuanced representations than what the bottleneck token can provide. Furthermore, the method's performance could be suboptimal in tasks that necessitate a broader contextual understanding beyond the immediate scenes, as indicated by the limitations of previous methods like May and SciAm-May. Lastly, in cases where the visual states of observed scenes are not sufficiently distinct or informative, ToBo may not achieve the desired level of performance, particularly in intricate robotic manipulation tasks.